So welcome back guys. Now in this session we are going to discuss about frequently asked questions for variable frequency drives. You can take these questions as your base mark or baseline for your upcoming interviews or any sessions in which you are going to present some sort of VFD related programs. So I hope this session will be important and very helpful for you guys. So let us not waste time and let us get back to this session. First of all, let me introduce myself. So I am Ishan. I am an electrical engineer. I am working in a company that is L&T from last 5 years, and I am having exposure of VFDs from last 5 years, and I am also having some sort of knowledge on troubleshooting and programming skills as far as VFD software or VFD control cards is concerned. Okay, so if you are having any sort of doubt, you can just email me on my ID with the subject YTQUES. Okay, so that it won't go into my spam folder. Okay, so without wasting further time, and let us start with this session. So the first question, very basic but important one: what is VFD slash VSDs? Another one which I want to add is VFC. Now most of you guys, if you are from diploma background, you haven't heard any of these names. So basically VFD, VSD and VFC are all one only. Okay, VFD is nothing but variable frequency drive. VFC is variable frequency converter, and VSD is variable speed drive. Now why these three names? Because companies like Danfoss, Wacom, okay, they all denominate those electronic items with the help of VFD. Okay, and companies like Schneider will have a denomination like variable speed drive. Okay, and companies like Parker will have names starting from VSDs, that is variable speed drive. So all in all these names are just one only. Okay, the meaning of all these names are from are all in all same only. So basically what is VFD? VFD is nothing but a speed controlling device which controls the speed of any motor. It can be induction motor also, it can be DC motor also, it can be synchronous motor also. But this what is the basic meaning of VFDs? That is frequency drive. Okay, there may be some speed drives which will control speed with the help of some other techniques, but here if you see the basic fundamental concepts of induction motor for speed control is by controlling frequency. Why? We all know the formula for synchronous speed is 120 into frequency upon poles. Now in a motor, here you can see poles are actually constant. Why? Because during manufacturing of the motor we are keeping poles intact. Okay, so we cannot change this number of poles in a later stage. Okay, so I am having this one quantity which can be varied according to me in my hand is frequency. So if I increase the frequency, my speed will increase. If I decrease my speed will decrease. So with the help of varying the frequency, I can vary my speed accordingly. So VFD is nothing but a speed controlling device which controls the speed of an induction motor with the help of by the help of changing frequency. Okay, so I hope this concept is clear. So next question, how does a VFD works? Now this can be very lengthy answer over here, but if we try to mitigate this answer in a shorter form, I can just explain with the help of 3-block diagram. This is my first block containing rectifier. The second block will be having filtering section. The third block will be having inverter section. Now here I will be having some sort of 3-phase constant frequency supply. Now here rectifier will convert input DC supply to output DC supply, but with some fluctuating or pulsating output. Now that pulsating output will be given to the input section of filter, which is basically a DC to DC converter, okay, in which there will be some parallel capacitor sort of configuration, due to which if I'm having input of filtering output like this one, it will pulsating one, so it will produce some output which will be some sort of this one. So this is actually filter. I have clipped these sections, so what I'm getting is some sort of filter output, which is smooth DC. Now this smooth DC will be working as a input section for inverter, which will convert my input DC supply to output AC supply. But here there is one catch, that is the output will be 3-phase variable frequency. So VFD is actually changing frequency by the means of these 3 blocks. Okay, so I hope this is very much clear, crystal clear. Okay, so the next question will be, what is the difference between VFD and soft starter? We all know VFD is actually a starter only, but now if you see there are actually 3 essential difference between VFD and soft starter. Now if you see the older generation starter, let us say DOL, okay, just the function of starter is to start the motor. Okay, so the starter will come into picture just for starting purpose, whereas VFD can be used for starting also, okay, it can be used from starting to operate the motor, to control the speed of motor, and to bring the halt, and it can be also used to break the motor. Okay, so if you see the essential circuit diagram of a starter, okay, and if you take a soft starter like thyristor starter, this all starter will be just used for starting. Once your induction motor speed reaches over 80% or more than 80% of the synchronous speed, the starter will be bypassed and it will essentially work as a free flow circuit only. Okay, so there won't be any sort of thyristor coming into picture once your motor has attained speed more than 80%. Okay, so you cannot control anything once your motor is started. So that is essentially a soft starter, whereas in the VFD you can control the speed. Okay, I am just writing in a short form so that you can just easily note down in bulletin points. So VFD can be used for controlling speed during operational mode. Okay, so these are actually basic differences of VFD soft starter. Okay, VFD and soft starter. Now the other thing is, in starter, if you can see that starter is just coming into picture for starting only, so there will be no effect of harmonics. Harmonics is nothing but a distorting wave which is affecting our fundamental frequency, whereas in the VFD is continuously clipping, chirping out our input supply, so there will be harmonics which will be injected to our grid. Okay, so this is one disadvantage of VFD, that there will be injection of harmonics into our grid. Now another question, different braking system used in VFD. Now I have mentioned you earlier, with the help of VFD I can control the speed and I can brake the motor. Okay, so how I can brake the motor? By the use of 3 techniques with the help of VFD. The first one will be dynamic braking. The other one is regenerative braking. Now here if you see, if you want to just clear these two things. Now in older technique I used to brake motor with the help of plugins, like if I'm having induction motor like this RYB, and if I'm rotating like this, okay, if I want to brake this motor, what I had to do was I had to change two wires. Okay, so this was essentially a reverse polarity, and it used to work as a plugging principle. But here there was one advantage: while in operation also power was getting consumed, and for braking also power was getting consumed even more. So this was not economical. So with the help of VFD we can actually dissipate the power without using it, or we can use the power that is being generated by the motor. How it is generated we will come back to in next question. So if anybody asks you what are the different braking system used with the VFD, that is nothing but dynamic braking and regenerative braking. In dynamic braking you will have a dynamic resistor, that is dBr. Let me write it down. In dynamic braking you will be having dynamic braking resistor. Okay, so this is the basic difference between regenerative and dynamic braking. So the next question is, what is dynamic braking? Dynamic braking is a method to brake the drive with the help of dissipation of energy that is being generated by the motor. So let us understand this dynamic braking principle. For that I am going to use one equipment over here, that is my lift. We all are having lift it at our homes or at basically in our buildings. So if I'm having one landing like first floor and 10th floor, okay, the first case my lift is standing on the first floor and I want to travel up to 10th floor. So we all know that my gravitational pulls will be downwards. So in order to drive the motor, my motor will generate torque. Now in this case, as I am going in the direction against the gravity, my motor torque will be greater than load inertia or load torque. So here my motor will be consuming power in order to overcome this load torque, so that my motor will travel to 10th floor, that is in upward direction against the force of gravity. Now in the second case, here let me write it down, it is motoring. Now in the second case my lift is standing over here, my lift is standing on the 10th floor, and if I want to travel downwards, and in this case what will happen, my gravity will also in downward direction, so my lift will essentially be dropped, okay, from certain height. So it will operate like a free fall stone from height. So we all know that in this case what will happen, my load torque will be higher than motor torque. So in this case what will happen, actually my motor will actually drive the my load will drive the motor. So my motor will be having an input mechanical supply, so that my motor will be generating voltage. Why? Because my motor will be working as a generator. Why? Because my load torque, if my load torque is more, so load will essentially drive my motor, so my motor will generate voltage. Now if you see the diagram over here, we are having input supply, you are having rectifier and it is producing some sort of DC voltage. So let us take this voltage as 560. In idle condition it will have a 560 volt. Okay, but now in the second case, load is actually driving my motor. Why? Because there will be mechanical input to the motor, so motor will generate voltage. So essentially you are having a power coming from input supply also, and over here my motor is also producing some power. So essentially due to this twin supply effect, my DC bus voltage will rise. What will happen? First thing will be DC bus voltage will increase. Now I need to limit this increase. Why? Because my DC bus is not designed to handle some abnormal voltage. Okay, I have designed my drive to handle some basic or some sort of limited voltage applications, like if my drive is of 800 volts, so maximum my drive can handle is 900 volts. I cannot operate a 800 volt DC drive in 2000 volt DC. Why? Because it will essentially damage my electronic components. Okay, so I need to dissipate the excess power. So what I'll do is I'll just connect one switch, that is electronic switch, and I will connect one resistor over here. So due to this thing, what will happen? Once my DC bus voltage will reach, like, let's say 600 volt, so my switch will be closed. Okay, so up to 600 volt my switch will be open. After 600 volt, let's say 601 volt, this switch will open and close like a chopper. Okay, so this switch is actually not continuous on or continuous off type. It is not NONC type. It is actually chopper will operate. Okay, so basically this switch is working as a chopper, DC chopper. So my additional voltage will be dissipated to the resistor. Chopper operated. Now next one is consumption of excess energy. Okay, so what is dynamic braking? It is a technique in which, with the help of braking resistors, my motor speed is actually getting controlled. So it is nothing but a dynamic braking. So let us come back to the next question, that is what injection braking. Now if you have heard about the methods of speed control, you have come across this name, that is disinjection braking. Here a DC supply is given to stator winding. In order to break the speed. Why? Because if my motor is in a rotational motion, okay, and in that case, if I give a DC current injection or DC current to the stator winding, so the magnetic field that is produced by the DC supply will actually try to reduce that speed. Okay, essentially what will happen, my rotational speed of the motor will decrease and it will essentially function as a brake. So the system in which there is injection of DC current in the stator winding and the braking resulting due to that effect, magnetic effect, that is nothing but DC injection braking. So the next question is regenerative braking. Now if you have traveled in the train, what will happen if you are coming from down the slope? If my train is coming in downward force, that is my gravity against with the help in the direction of gravity, what will happen? My load inertia, in the first case, if you have just watched that dynamic braking section, I have told you that when my load torque is more than motor torque, in that case my motor will be working as a generator. Okay, so when my train is coming in a downward slope, the load torque will be increased, that is load torque will overcome the motor torque. In that case my motor will be acting as a generator. Whereas in dynamic braking we used to connect a resistor, let me write it down. In dynamic braking resistor is used so that the energy that is being generated by the motor will be dissipated inside the resistor in the form of heat. So that is actually we are wasting that energy, we are not using it, or we are not storing it. Whereas in regenerative braking, the energy that is being generated by the motor is being fed to the grid. So let me write it down, interview answer. In regenerative braking, energy drive is utilized in the grid. Okay, so the example of this is train, locomotive. Why? Because in a downward gradient, the slope gradient, if the slope gradient is more, okay, this is my pantograph. Now here you are having this G like this, that is 9.8. okay, now if my train is going downward, so the load torque will be more than, okay, it will be more than the motor torque. So the energy that is being generated, it will be fed back to the grid. Okay, so due to this effect, we are actually if my one train is going downwards and other train is going upwards, so the energy that is being generated by the motor of the locomotive, that is being consumed by another locomotive. So this is the never ending process, that is regenerative braking. In this section, in this regenerative braking, we are actually using that energy, we are not dissipating it, we are actually using it. So that is nothing but a regenerative braking. Now we have talked about some many different applications over here. That is, one of them was, I think, lift, another one was train. So we have seen some application for different torque also. So what are different type of load for VFDs? So there are basically three loads. I want to section them out. Like, one of them is constant torque load. Other one which I want to mention is variable torque load. Another one is shock load. Now what do you mean by constant torque? In which the demand of torque will be constant. So the example will be crane, okay, lift, escalators, in which the demand will be constant throughout. Okay, so there is no abnormal variation in the torque requirement for the motor. So the application in which VFD are installed for the constant load will be constant load VFDs or constant torque rated VFDs. So the second section is variable torque load. The name suggests the load will vary depending upon the torque. Okay, so if you see the pumps or high speed fans, in which the torque is proportional to the load, but in square. The function will be square, so it will be like this. Okay, if my torque is increased by 1%, or if my load is increased by 1%, the torque requirement will be increased by 2 in the square of that particular value. So here the torque load relation will be exponential, or the function of x square. Okay, so these are actually variable torque loads. Now the shock loads, like in many applications there is a requirement of shock loading. One of the best examples of shock loading is hydraulic press or motor hammers or extraction pile drivers, in which hammering is done with the help of electrical motor or rope operated winch. So in those cases I need to have a shock loading rated motor. So these are basically three applications of constant of loads. One of them is constant load, other one is variable torque load, and third is shock load. Now the application of constant and variable and shock loading torques. So let us go through this table. Now these are the agitating applications. So you will be requiring a variable torque over here. Another one is blowers, centrifugal blowers, that is high speed fan, which will be having variable torque. And if you are having a fixed fan like home application fan, then you will be requiring a constant torque. Now coming to the compressors, if my compressor shaft blade is mounted in an axial fashion, I will need a variable torque. If my compressor, that is piston, will be having reciprocating action, a rotary action or a rotational action, then my speed or torque requirement will be constant. Now coming to the belt conveyors, all of the conveyors will be having a simple loading only, so all of them will be working in a constant torque. Now coming to the fans, as you know, if my fan is in axial mode, I will have a constant torque applications. If my fan is of centrifugal type, in which I need to suck something using the help of centrifugal action, those type of requirement will be requiring a variable torque applications, VFD. So you can go through this another application of constant torque and constant horsepower. Okay, mixer and pumps. You can easily find out basically different typical different loading impacts on the VFD, and you will also have a breakaway torque, okay, which you can relate with your torque speed characteristic diagram. Okay, so you can just take a screenshot of this in order to have a basic clarification on applications of different load. Okay, now what do you mean by torque speed curve? Many of times what happens in your technical interview round or technical examination, basically you will be given some sort of graph, and in that graph you will have to denote some loading. Like if I am giving one application that I needed VFD for lift, okay, and I will be given some graph like this, okay, and you will be given some section like this. Okay, x1, x2, x4, and you will be asked that in which region I need to operate my lift, in which of this region. If you select the x, that means this one. Okay, so in this type of questions you need to observe the question demand, and you need to apply your basic fundamental skills over there. So here, if I let us draw first some basic graph over here. Okay, so in the x-axis I will be having synchronous speed, in the y-axis I will be having a torque. Here you are having the 0. Now we all know the basic torque speed graph will be like this. Okay, just let me shorten this one. Okay, so this is actually typical torque speed characteristic. Now if you see over here, just let me again redraw this. Okay, just a minute. Okay, so these are typical torque speed characteristic of 3-phase induction motor. Okay, so here if you see, you can divide this graph in two sections. One of them is up to this section, another one is this section. Okay, now if you see over here, your average torque will be almost constant over here. Okay, there is no variation, abnormal variation. So this section, okay, this section is actually constant load section. Okay, so in this section you will get a constant torque. Now if you operate your induction motor in this section, you will have a constant torque. But if you need some sort of variable torque, okay, so you can operate your motor from this region to this region. So in the graph will show you two different regions for operation. One of them is constant load and one of them is variable torque, because if you see over here, this point and this point, you are having some surge over here. Okay, let me draw. Okay, you are having surge over here, you can see some spike. Okay, so this shows from this area to this area you will have a variable torque. So if I ask you an application oriented question, that if I want to operate a drive for lift, in which section I can operate, section 1 or section 2? So you know that lift will require a constant load application, so you can just type out the answer by I will operate my lift in section 2 region. And if I'm having some other questions like tell me in which section you will operate pumps, centrifugal pumps, so you know that centrifugal pumps require a variable torque, so you can just answer out by I have to operate my VFD in a variable torque region for pumps. So with the help of this diagram, you can easily understand what sort of requirement my VFD will need in order to suffice that load. Okay, so now coming to the next question, this is basically very I can say simple questions out there. Out of these all questions, this is the simplest question which you can be asked. Okay, so what is slip? So slip is nothing but a difference, or what I can say, the unit difference between your synchronous speed and your motor speed. Now synchronous speed is nothing but a rotating magnetic field, correct? No, ns is nothing but a speed of rotating magnetic field inside the air gap. And your, sorry, I have written over ns couple times, so it is ns minus n actual speed. So the slip is nothing but a difference between synchronous speed and actual speed of the motor. Okay, so this is a basic question for electrical engineers. I hope interviewer will not ask you this, but if they ask you, you should be able to give them the answer. Now coming to the follow-up question. Okay, if you are asked that what is slip, you don't get too much excited, because they will be having some sort of follow-up questions which they will try to trap you over there. Okay, so what is slip compensation? It is actually a feedback system for closed loop VFDs, in which drive will measure. Let us draw the functional block diagram first. This is your rectifier. Okay, so you are having input AC, and here we are having output DC, and that DC input is going to the inverter. So the slip compensation is essentially an open loop control technique by which the drive will measure the current, that is output current, and compensates the slip by increasing the voltage and frequency applied to the motor. So here you are having a motor as an output. Okay, so here you will be having some feedback from the motor that will be given to some comparator. Okay, and if your rectifier is of semi-control type, it can regulate those SCR or thyristor, or else it will control the firing angle of inverters. Okay, so in this section, your slip will be adjusted according to your load current. If my load current is high, it will adjust slip accordingly, because if you see the torque speed characteristic, if I increase my load, my speed will decrease. Okay, and my slip may be increased. Okay, so I need to compensate those things. Okay, so this is the open loop method that is used to control the input supply voltage or output frequency in order to balance the V by F ratio, and due to those ratios you will have a slip compensation as an output. Now what is sensorless speed control? This is actually very important, what I can say, important topic as far as VFD is considered, but as far as interview is considered, we are just going to know about the basics over here. So sensorless vector control is for constant torque application only. Okay, it is just used for constant torque application, in which the drive will deliver maximum torque, okay, by controlling voltage and frequency of the motor. Okay, it is nothing but a effective system for maximizing torque by maintaining V by F ratio. Okay, why? Because if you increase the voltage and increase the frequency, there will be unbalanced magnetic field. So in order to maintain the magnetic field inside the rotor or stator or air gap between the stator and rotor, you need to control this ratio. So I need to either, if we increase the frequency, I need to decrease the voltage, and that will be actually vice versa, in order to keep the magnetic field same throughout the operation. So that is nothing but a sensorless speed control. Okay, because here you are not having any sort of feedback from the drive. It is just measuring the output frequency and output voltage. Now the role of encoders. I will be preparing some detailed video on encoder, which you can just check out over there, but I will just give some glimpse of encoder over here. Encoder are the device used to measure the speed and generate pulse. Okay, so these are nothing but elements which are used to measure the shaft speed of the motor. Okay, and why speed is required? Because I told you the slip is essential for induction motor. Slip is nothing but difference of synchronous speed minus actual speed. Okay, I know the synchronous speed with help of formula, but how I will know the n, that is actual speed. So for measuring the actual speed, I need to have an encoder. Okay, encoder will measure the speed, and it will give some sort of feedback to the VFD in order to compensate for the slip of the motor. Okay, for various load, in order to achieve the accurate speed output. Now encoder is also actually tacho generator. Okay, if somebody just replace the name of encoder by tacho generator, so essentially encoder is nothing but tacho generator, that is tachometer, electrical tachometer. Okay, now this will be having some sort of pulsating output. Okay, now the maximum pulsating output will be your bandwidth capacity of the encoder. Okay, now here your bandwidth of the encoder should be equivalent or less than your logic bandwidth of VFD. Okay, that means if I want to just explain you with a different or simpler meaning, if I'm having some sort of capacity of a motor, like let's say 300 rpm of motor I'm having, and if I'm having a drive, okay, which starts the speed from 300 rpm and it can take up the speed from 300 to 500. Okay, so there is one clear difference over here. My maximum requirement is 300, but the drive I have selected for the motor starts from the 300, so there will be mismatch. So the same way, not in the exact same way, but the fundamental way, if my encoder can count the pulse of 30 rps, okay, and if my logic can only count up to 28 rps, 28 revolutions per second, okay, so what will happen? There is clear difference of 2 rps. That means my drive cannot measure those 2 revolutions. If I'm having encoder which can rotate, or which can generate 30 pulses per second, and if I'm having some sort of feedback system or measuring system inside the VFD which is having maximum capacity to read out the 28 pulse per second. So I will have some sort of false output from that sort of feedback. So this should not happen with my VFD. So in that case, while designing encoder or while selecting encoder for a VFD, I need to check out the bandwidth capacity of my VFD. That means my pulse speed of the VFD, and I need to check out for the bandwidth capacity of that encoder. These all things will be available inside the encoder itself. So while purchasing or while deciding encoder, you can just check out the bandwidth capacity of that encoder in order to choose the correct encoder. So with this session we have completed this session. You can just like and comment to my channel, and we'll get back to some other videos in upcoming sessions. So I am having some sort of plan for a detailed VFD session. So in that session I am going to cover some detailed theories on encoders and pulse width modulation and pulse and amplitude modulation methods. So have a nice day. Goodbye. If you have any sort of doubt, you can just reach up to me. I have already mentioned my mail ID. So have a nice day ahead. Goodbye.